Okay, so we are finished with Chapter 8. We're on to Chapter 9. So the exam, folks, will cover maybe a tiny bit of Hess's Law from Chapter 7. Maybe. Chapter 8 loves Gibbs free energy. And then 9 is physical equilibrium. There's two kinds. There's chemical and there's physical. Chapter 9 is physical equilibrium. And so I'm hoping that we get it completely finished. So we have a bit of a dilemma. Yes, I know. Do we have class Tuesday?
Yes. Yes.
So there will be no class for my Monday class because it's a holiday. I'm thinking that on Tuesday I will have class, but for part or most of that class I will give a lecture on global warming. Okay. Once again, it's something that you folks as students of the world need to be able to discuss that with some background. And so that is the plan as of right now. So unless you hear differently, we will meet on Tuesday, and the lecture will, and I don't know, I promise you this, okay, there will be questions about global warming on the exam. So it's not like this is a lecture that you can afford to miss, okay? It's just a lecture that it's easy for me to give, all right? And if it turns out that we are falling a little bit behind or more behind, then I'll also slip in a little bit of real chemistry, okay? All right. So, lasers give me some problems here. Okay, so physical equilibrium. I've tried to come up with some analogies for equilibrium. So what we say is the state in which competing processes are balanced. So what do we mean by that? We mean that as many people are coming in the door or this room as are leaving. Okay? If I were to ask you if there were 10 people a minute coming into the room and 10 people a minute going out, and I said what is the net change of people coming in and out of the room, the answer would be 0. Okay? That would be a dynamic equilibrium, where coming in and going out is balanced. What happens tonight at midnight when there's nobody in here? What is the flux of people coming in and out? 0. So you can't always use the, what does it say here? Lack of change is consequence of an equilibrium, but not proof that there is an equilibrium in the system. Okay? So it looks like nothing is happening. In some cases nothing is happening, in other cases it is happening. So last night I had a heckler in the crowd who didn't buy into this, because this is a bell jar, and this would have like a rubber seal down here so that there's no way. It's a closed system. Okay? Closed system. And if we have liquid water right here and we let this sit for long enough, okay, we will end up with whatever the temperature is in the room. If it's 20 degrees C, then we're going to have about 20 torr. Okay, 20 torr of water vapor in the air here. Now folks, this chapter, we deal with gases again. Okay, so you need to be comfortable understanding what a torr is, what an atmosphere is, what a kilopascal is, all those things, okay? So in this case, I learned torr, okay? I learned torr, and I learned that there are 760 torr in one atmosphere, okay? That's the rule, okay? So 1 atmosphere equals 760 torr. So out of 760 torr, only 20 of them are water here. Now I can make more water go into the air here by heating it up. Okay? The vapor pressure of water at 20 degrees is about 20 torr. If I go to 30 degrees, I can make it even bigger. Okay? So, I have liquid water here. I have a seal here. I let it sit long enough that there's no more water coming out of liquid. But guess what? What you don't see is that there is actually water coming out of the liquid. Dang. Uh-oh. But it's being balanced by the amount that's going in. Okay, the air can't hold anymore. It's kind of like this room. We fill it full, and you can't cram any more people in until somebody leaves. And that's what's happening here, okay? So we have water leaving the liquid phase, and we have water from the gas phase going into the liquid phase. You cannot see it, but that is exactly what's happening. In fact, when you have a drink with ice in it, okay, this ice can be minus 20, minus 30 degrees. Okay, ice cubes are cold. It's sitting in this water, and as long as you're stirring this so that it's all mixed up, the temperature of that water, geez Louise, is 0 degrees Celsius. The water is 0 degrees Celsius, and you've actually got water molecules that are liquid form that are jumping into the solid, and vice versa. You're at equilibrium there. Now, you're going to see this a couple times today, and I think it's in there too much, but once again, solid, liquid, gas, 3 phases. You know that. What do we call it when we go from solid to gas? Okay, and when we go from solid to liquid, we call that melting. I mean, you can call it whatever you want. We'll go from here to here. What do we call that? So, you know, we'd call it vaporization, we call it evaporation, and how about when we go this direction? Oops. Okay, we call that condensation. That's about the only thing that I can think of it being called. Vaporization and evaporation here. And then back down here, we would call that freezing. Okay? Now, Hess's law tells us that if I give you what the sublimation energy is, and I give you what the heat of fusion is, you can figure out what this is, okay? It's a state function. I can go from here to here and here to here, or I can jump all the way. Now these folks, these are temperature kinetic energy curves. And so if we look at this one, this is at temperature 1, this is the number of molecules, and if we say that E1, anything above E1 has enough energy to actually jump out of that phase. Okay, so let's just go liquid and gas. So we look at this distribution here at this temperature, we have a small amount. If we take the integral of the area under this curve, there's a small amount of molecules, I don't know, I'd say maybe 5% or 3%, you can estimate, of molecules that actually have enough energy to jump out of the liquid phase. As we heat it up, the distribution flattens out. Okay, so this doesn't have nearly as many molecules with this one particular energy level. It gets spread out more, but then this tails out here. Now look at how many more have temperature or have energy above E1. It looks like it's about 1/3 of them. Okay, so it is this little bit right here, this little bit right here, that tells us how much of that particular molecule has the energy to go from one phase to another. This is a lecture on phase change. We're going to look at phase diagrams, okay? And we know this. Greatest order solids, least order gases. So this is a, if somebody else can come up with a better analogy, please do. But this is the rate of evaporation. If I were to pour some water on the floor in this room, it would start evaporating, and it would evaporate at the same rate. Okay, got as much water molecule, gaseous water molecules jumping out of this liquid as we'd have just a lot of it. Okay, that's this. However, the rate of condensation is nothing. Okay. It's not until you start reaching this equilibrium level where you start actually having liquid have gaseous water going back into liquid. What I'm trying to say is that once you're here, you can't observe any change, okay? So I came up with an analogy of concert bathroom analogy, okay? So how many of you have ever been to a concert? Okay. So do you think there are more people in the bathroom during the time that they're singing or when they're taking a break? Or like a baseball game, okay, or a football, something, okay? So this is like the line of people going into the bathroom, okay, at the break. This is the line of people coming out of the bathroom. There's nobody coming out in the beginning. But then you start having more and more people coming in because you've had all these people going in. And eventually, you got the same number of people coming in as you got going out. Okay, just like I said with this room. So that is when we are at equilibrium. Dynamic equilibrium is right here. This has to catch up. The rate of condensation has to catch up right here. Okay? If, folks, I poured something on the floor, some water, and it starts to evaporate, if I then do something where we just pipe in a bunch of vaporous water vapor, we can make it so that that water on the floor never evaporates. It's kind of like being in Florida or in the tropics in the summertime. How many of you sweat? No, never mind. I sweat. Okay? And it's a wonderful thing to be able to sweat if you got plenty of water to drink and if you live in Arizona. Okay? Sweating is not such a fun thing to do in southern Florida or in the tropics. Okay? And that is because if it's dry, what is the heat of vaporization for water? 40.7 kilojoules per mole. Okay? A mole of water, folks, is like, you can put 3 or 4 moles of water in your mouth. Okay, that's how much it is, okay? I can sweat probably like about a mole every 5 minutes. I swear, okay? So think of that. If I've got all this water on my body, and I'm in Arizona, I still need to be able to give energy to the water molecules to go from the liquid phase to the gas phase. Okay? So where do they get that energy from? My skin. Energy from my skin, my body, goes into that water molecule and allows it to jump off of Don Blake. Okay? And with it, guess what? 40.7 kilojoules per mole. So if it's dry and I got water all over me and I'm evaporating, I'm losing every time, in theory, every time I sweat 18 grams of water, I've lost 40 kilojoules of energy. Okay? The problem is that I sweat the same whether it's dry or not. So if I go to Florida or I go to Tahiti or to Trinidad or something like that, then I'm sweating, and guess what? The water vapor in the air is so great that I am in equilibrium. Okay? I'm not evaporating at all. I've got, my molecules are jumping off, but other ones are jumping on. So I don't cool down. How many have ever been in a place where you feel that sweating didn't do you any good? Okay, then you know what I'm talking about. Okay? So that's what is happening right here. As we get closer and closer where the vapor pressure of the room or where you're at is nearly saturated, this is the region that you're in. It's an equilibrium. Okay, I think I just said a bunch of stuff here. Okay, so don't write this down. Okay? You should know this. Okay? We just sort of did it. That what do we call these different things? Okay? Jeez. These, once again, are the different heats of things. Maybe I should use this. So here we've got liquid water going to gaseous water. That takes a lot of energy. Solid water to liquid water takes some energy, but not nearly as much. And generally speaking, folks, the heat of fusion is less than the heat of vaporization. Why? Why, folks? I'm not going to ask you this on an exam because it'd be too hard to grade. But why is it that, generally speaking, the heat of fusion is less than the heat of vaporization? So, if you have an ice cube, okay, it's ordered, correct? It's ordered, there's interaction there, and so on. Once you go to the gas phase, those molecules never see each other again. Okay? Are they getting any stabilization from hydrogen bonding and stuff? No. So folks, generally speaking, gases, we just talked about entropy last week. Okay, gases have more entropy than a solid does. So generally speaking, this is a rule. And it's because, as I just said here. Okay, boiling points. This is just an indication once again. We're going back to chapter 5 or whatever for molecular forces. I might have even shown this. Something like argon. Argon is just one atom. Okay, it's not a diatomic, it's just Ar. You put a bunch of them together, you got argon gas. The boiling point is 186 degrees below zero. And look at this. Does it take much energy to vaporize it? 6 kilojoules per mole. That is not much at all. Look at mercury. So let's look at water. We know this about water. The boiling point is 100, and I just said that this is 40.7. Okay, water. And why does water have this high boiling point and this very high heat of vaporization? Because of hydrogen bonding. And yet if we look at something here like mercury, which is just mercury, just Hg, get a bunch of it, stick it together, you got a blob of mercury. Look at the boiling point, 357. Much higher than water. And look at the heat of vaporization. What's mercury got going for it? It's just got dispersion. Only dispersion. Okay? Whereas water has hydrogen bonding, it's got dipole-dipole interaction, and it's got dispersion. But this thing is heavy. 200 grams per mole, lots of electrons. Now, last night, I was shocked. I was shocked that people didn't know this. Yeah, I'm going to read this to you. And I want you to pay attention to what I'm saying. That the normal boiling point is the temperature at which a liquid boils when the external pressure is 1 atmosphere. What that says, folks, is that everything boils at 1 atmosphere. Okay? Everything. Now, the boiling point temperatures are different. But everything, the vapor pressure of anything, when it boils, is 1 atmosphere. Or 760 torr. Okay, or 101.3 kilopascals. Okay, whatever units you want to use. And I had people last night that were just dumbfounded by this. They just didn't understand what boiling was. Okay, fusion, big deal. Okay. How many times have we seen this? Several? Can I have a several? Okay, thank you. Thank you. This is not the kind of thing I would give you on a midterm. But it is exactly the kind of thing I would give you on a final, where you have 2 hours. Okay? I could ask you to explain this. Geez, I don't know if I've lost my power or what there. I might ask, could you go to the stock room? I might need some of these, the AAAs. I need 2 of them. Thank you. I'm not sure if this is going to solve my problem, but it'll make me feel better. Okay, so in here, folks, okay, this is where you have a piece of solid. In this case, we're just going to say it's ice. This could be a lot of things, but we're going to say this is ice. So this is all solid ice, solid, 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 just warming up. And then, folks, it doesn't change. Temperature stays at whatever this heat of, whatever this thing is going to melt at. If this is water, it's 0 degrees. Stays same temperature, you accumulate more and more liquid water here, and then all of a sudden, boom, you got liquid water just warming up, and then you have this as the vaporization part, okay? You need to be able to, you need to understand this, okay? It takes energy, folks, to make this happen. You got to put this on a stove or something, or set it in a room if you're below 0, and let it warm up. And then it slowly melts sitting on the table. And then, so, where on here, folks, where on here, if this is an ice cube, okay, and I put it on this table at the beginning of lecture, okay, and we start right here, okay. If I had a laser that worked, I would have somebody point. Where, folks, on this curve, where on this curve do we end up at the end of class? Okay? I'm going to ask somebody to come up, go to that computer, take that mouse, and put that cursor where we end up, because I don't have a laser pointer. You do it. I'm scaring the heck out of this young woman. Okay, she's going to come up. Let's see if she's right. How many envy this woman right now? Yeah, right. You got to just shake it around a bit for it to, there you go, okay.
Because
right there.
It's not full of water in the air.
Perfect. Look at that. You see where she put that thing? It disappeared.
Oh.
Somewhere in here. I think it's too high. Good job. Okay, I would probably put it right about here. If this is 100 degrees, very nice. Thank you. If this is 100 degrees and this is 0, you know, we're probably going to be somewhere right in this area right here, okay, for the water. Thank you very much. Okay, phase changes. That's what we call it. Changing phase. Sublimation, blah, blah, blah. Now, how many knew this one? Deposition. Okay. How many knew deposition? Not a lot of people use that term. Okay. We actually use it in atmospheric. Okay. And things, deposition actually happens on plants. Okay, in buildings and stuff. Okay, I don't think we need to know about that. We know about that. Already talked about that. Hess's law doesn't. Okay. You are going to, probably on the exam, certainly on the final, need to explain this. Okay? So I will explain it to you right now. This whole chapter is on equilibrium. Okay? So this is the vapor side. This is the solid side. That is the liquid side. If you fall on this line, you are in equilibrium between whatever's on either side of you. Okay? So what that means is at this temperature, this is temperature here, this is pressure here, at this temperature and pressure, we are in equilibrium between solid and gas. Now who would have thought that? Here's my ice cube. Okay? Do we see any liquid water on that ice cube? No. Do you? No. Okay, this is a fresh ice cube. Okay, not one that's melted much. It's got a temperature right here, and that pressure, okay? Look at that, right there. What that means, folks, is that we are in equilibrium between the solid and the vapor phase. Vapor, who'd have known that an ice cube gave off vapor? Well, that's what this says, okay? So we follow this thing all the way up. And eventually we get, this is kind of drawn kind of weird, we get to a point where right there, at that point right there, folks, we are at equilibrium between three phases. Liquid, solid, and gas. That's the only time when we can have it, and it is right there, and we call this the triple point. And right there, folks, is where you have all three at equilibrium. What would delta G be there? Right. So, if you follow, then, along here, if I told you, okay, well, here's a question. What are you? You're right now, you're an H2O, each of you. Okay, you're an H2O. And I want to know, what are you at 0.5 atmospheres and 60 degrees? So I'd say 0.5 is like right about here. 60 degrees, I'm guessing, is right about there. What are you? You're liquid and vapor, right? What if I was a little bit wrong on that and 60 is right there? What are you? Liquid, okay? So on the exam, folks, you're going to have to, I'm going to give you temperature and pressure, And you're going to have to tell me what you are, how many phases you are, what you are. Okay? Now, what's interesting is this is for water. Okay? Water is weird in that the slope of this line is a negative slope rather than a positive slope. Almost all other things go this way, but not water. Okay? And so what this means is that if we have something that, let's say, is below 0, okay, so let's say that right here, let's say that's 0. If my finger right there is at -5, okay, at -5, what is the minimum pressure? What is the minimum pressure at which water is in equilibrium with, like here, if you can fix it, thanks, with liquid and solid? So -5 degrees, what pressure? So don't forget this little dotted line here, this is 0 degrees, okay? So what temperature, if this is 5 right here, what pressure do you think you'd have to be at? Maybe, I don't know, is that 1.5 atmospheres or 2 atmospheres or something like this? So you can actually, by applying pressure to an ice cube, you can make it turn to liquid. Okay? Because look at this. What if, is it working? Yeah. Oh, thank you. What if we're right here, we go up like this. So at 5 degrees below 0, I got an ice cube. I start applying pressure to it, boom, 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 and guess what? Right about there, you start being in the liquid phase. Okay? Most gases, or most things, go this way, that the more pressure you put into them, they become a solid, but not water. So water is special. So once again, you're going to need to know, phase-wise, where you are on this. Here's CO2. Okay? Look at CO2. What is CO2 famous for, besides like parties? Okay?
Dry ice.
Yes, dry ice. What do you think dry ice means? Do you ever think about what does the term dry ice mean? It means it never becomes a liquid. At least I think that's what it means. Okay, it's ice, it's cold, but there's no goo, there's no mess. Okay? Look at why. At 1 atmosphere. What world do we live in? Do we live in a 1 atmosphere world or a 2 atmosphere world? We live in a 1 atmosphere world. So 1 atmosphere right here, look at that. 78 degrees below 0. Okay, that is right there. What does that phase change right there mean? If you warm up, you're in the solid, 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 all of a sudden you're equilibrium, and boom, vapor. Okay? That is the vapor phase. So you cannot have liquid CO2 at a pressure below 5.1 or 5.2 atmospheres. There's no liquid right there. You go from here to here, all you hit is solid, vapor, solid, vapor, solid, vapor. Okay? Up above here, solid, liquid, vapor. Okay? So once again, folks, you're going to be given temperatures and pressures, and you're going to have to tell me what phase you are at. Now, we're going to get into this a little bit later, probably not today, but next week, on how do we change boiling points and stuff. Okay? If this is the normal curve, we can actually decrease the melting point. We can actually make it melt at a lower temperature and boil at a higher temperature. And we're going to learn the equations on how we do that. It's all part of molality and molarity, okay? We're going to be studying a lot about mole fraction and that kind of stuff. So folks, you know I love moles, right? I love moles. And so you got to know you're going to get moles, okay? So I love this kind of stuff. Okay, phase diagram. This is just stuff your book gave me. So once again, this is for CO2, okay? This is for CO2, pressure of CO2. So this point right here, if we're right here, folks, we are, 1 atmosphere is right about it here. Solid to gas, solid to gas, solid to gas, solid to liquid to gas. Okay? The triple point, once again, where we're at equilibrium with everything, is right there at 56.6 below and 5.1 atmospheres. So, if you are at that pressure and temperature, and you warm up, don't change the pressure at all, you warm up, what do? What phases do you go from? Liquid to gas. I want to hear you say that, okay? Next time there's a line that goes up. Oh, what's that? Oh, you're good. You're good. Okay, answer this. What do you think it is? Oh, everybody gets an A today. Water. Look at that. You went from solid to liquid by increasing the pressure. Okay, do this. So, this is kind of a cheesy question, but so what? So there is the water, the water curve, okay, versus temperature. You see that right there? Does that look like this? Does that look like this? Does that look like this? Okay, I want to show you a very, very impressive job of animation, okay? I'm old. Huh? Well, don't be too impressed because I didn't do that. But that's as animated as things are going to get here. All right, now we come to the good part. Okay, the rest of that was just entertainment. Okay? This now, look at the vapor pressure versus temperature. Vapor pressure and temperature. And there's 1 atmosphere. Okay? So I'm asking all of you. Okay, diethyl ether. What is its boiling point? What is the boiling point of water? What is the boiling point of mercury? Amazing that they are all, when they hit this 1 atmosphere line. Last night it was a shock to several. They just didn't understand that that's what the definition of boiling point means. And I'm not making fun, if it was the first time that you've understood this, fine. Okay, that's what I'm here for, is to teach you. But folks, that is the definition. When the boiling point is 1 atmosphere, 760 torr, 101.3 kilopascals. Okay? That's the same thing. One of my favorite, you can ask Josette and Aaron. Okay, they took a class from me as graduate students. I guess Aaron took it as an undergrad. Anyway, I love this equation. This is one of my top 3 equations of all time. So what do you think I want you to do? I do not want you to memorize this equation. I want you to look at it. It's a trick. Look at it well. Look at it good. Which is it? Look at it well? I thought that had to do with like health. Any English majors here? If so, you're in the wrong room. Because I would be in the wrong room if it was an English class. Okay, so log P is equal to delta H of vaporization over RT plus some constant. It's called the Clausius Clapeyron. I'm not sure. Okay? This equation will do you absolutely no good. Why? Because L log of P. What if I give you the temperature and the pressure and I ask you to figure out the delta H of vaporization? Can you do that? No. You cannot do it, folks. You cannot have a unit inside a log. You cannot take the log, you can take the log of 6, sure. Can you take the log of 6 pounds, 6 psi, 6 torr? No. Okay? This equation, folks, needs to be made user-friendly. Okay? And I could ask you, I could be mean and say, okay, oh, well, let me just do that. Sure. Okay? Get those calculators out. So, here's what I want you to do. I'm giving you that the delta H of vaporization is equal to, let's say, like water, 40.7 kilojoules per mole. R is 8.31, and T is, let's say, it's 300 Kelvin. So 300 Kelvin, 8.31, and 40.7. Okay? What is the log of P? Or what is P? I want to know what is P. So, T is 300 Kelvin, 8.31 degrees liter atmosphere, or degrees per joule mole, and delta H vaporization is 40 kilojoules per mole. Who's got an answer? Don't worry about C. That's just a constant. Okay, so what's the answer? 1.016. How many got that? Okay, 1.016 what? Oops. No units. That equation does you no good, folks. It's almost like entropy. Okay, entropy is not so easy to calculate. Change in entropy is. Okay? So if we rearrange this, it looks like this. No, that's the original. There it is. Don't write it down. This is the Clausius Clapeyron equation. Let's just look at it. Don't write it. There's a reason I say don't write it. So now, folks, you got a P1, P2. So if you've got a log here, folks, it's not a problem. Because as long as you've got the same units, as long as P1 is 10 atmospheres and P2 is 4 atmospheres, atmospheres cancels. And you just look at what is the log of 10 over 4. Okay? So this now works for us, and this now works for us. Okay? So let me ask you this. How many parameters in this equation? How many unknowns? Jessica.
One, 2, 3, 4, 5.
5, she's right. 5 that are unknowns, or that are things that are variables. Okay? So in order for me to ask you to calculate one of these, this, or this, or this, or this, or this, you have to be given 4 of them. Right? I can't ask you to solve this if I just say temperature 1 is 300 degrees and temperature 2, and pressure 1 is 1 atmosphere. You can say, I need a whole lot more information than that. Okay? Now, why do I not want you to write this one down? Because, folks, this can be rewritten. Okay? It's very subtle. Very subtle. There. The only difference is a negative sign here. So I can't remember this one. I can't remember this one, okay? I like to have whatever this number is, P1 or P2, I don't care which, is the one that starts here. Okay? So you can rearrange that to this. Okay? Write this down. So what this allows us to do is to predict a vapor pressure of something. Okay? So P2, P1, notice this is a minus sign now. Once again, I can only remember this equation by knowing that whatever's on top here is the first one here. So it's going to be P2 over P1 equals minus the delta H of vaporization over R times 1 over T2 minus 1 over T1. That is the equation I prefer because I'm too old to remember it the other way. Okay? Simple fact. Okay? So, this is the equation, as I say in the next slide. Here. Okay? Now, you can use whatever you want. Okay? I will show you in a minute you get the same answer. But this is the only way I remember it. Okay, so do this. Take your calculators out, folks, and do this. Don't sit there and let me do it for you or your neighbor do it for you. The more you do these, the better off you are. And look, I'm such a nice guy, I gave you the equation again. I will not do that on the exam. So you should, folks, be comfortable enough with Clausius Clapeyron to be able to do that equation, to do this problem. You know, this would be a 8-point question on an exam. So you should be able to do it in about, 4 minutes or less. Okay, who's got an answer? Okay, first of all, looks like you're still working. Okay. So what was the vapor pressure at 34.9 degrees? I gave you that. What was it? Are we still doing this problem? What a bunch of slowpokes. What? They can't help it? Okay. Whose side are you on? Okay, who's got an answer? Raise your hand. Jeez Louise. Okay, these guys do. What do you get? Negative 2.6. Does that make any sense at all? The boiling point is negative 2.6. The boiling point of that stuff is negative 2.6. So, thank you. I asked him to give me the wrong answer. Just so you know. Did you use Kelvin?
Yeah, I was Kelvin.
Oh.
Wait,
How?
no,
That was in Kelvin. Well, then you can't get below 0 Kelvin. And usually, if you got a vapor pressure of 100 at 35 degrees, when you go to 760, the temperature is going to get a little bit warmer. So folks, I'm giving these guys a hard time, but what you want to do is you want to see, does your answer make sense? Okay? If 35 degrees is the temperature at which you're at 115, you should just be able to estimate. Okay? How about you? What do you estimate the boiling point would be? 50, she says. Okay, it could be 50. I think it'd be warmer than 50, because this is only about a sixth of an atmosphere. You got to go all the way to 760. Okay? 760, folks, is boiling. Okay? Yes? 324, he says. What'd you get?
350.
350, he says. Okay. We're getting, those make sense. Each of those makes sense. Okay? It's got, okay, so first of all, you can never do negative. So the reason I asked these guys if they had used Celsius, because that, if you use Celsius, you're screwed. Okay? Never use Celsius. It's always Kelvin. All right? So I'm going to put the way to solve it up. And then I want you guys back, or the guy that got 320 or something, the answer is 350. Okay, the guy that got 320, I'd like you to look at this and see, try and tell me what it was you did wrong, okay? How many got 350? How many now look at this and see how to do it? So who didn't get 350? Raise your hand. Okay, what'd you do wrong, Nancy?
I changed atmosphere.
Okay, so folks, do not change units if you don't have to. Nancy changed this into atmospheres. Why? As long as you've got the same units, okay? You had 150, what did I say, 115 torr, and I gave you 760 torr. So all you got to do is go 760 over 115. Why change 115 into atmospheres and then change the other atmospheres, right? Who else got it wrong? Yes? You didn't convert to joules. Oh, so you had, oh, that's a good one. Okay, look, we got joules here. This is kilojoules. Okay, that's why I've got this times 10 to the 3. So that's another one. So folks, if you don't convert to Kelvin and you don't realize that this is in joules and this is in kilojoules. So you guys back there, do you make any of those mistakes? Joules. Okay. So what you want to do on an exam, folks, you know, I've tried to get you to get a sense for what the answer should be. Okay? So these guys here did everything right, and they did it fast, but they just were off by a factor of 1,000 here, which makes a huge difference. Okay? Huge difference. So if you get a negative value for temperature, you got to go, oops, that can't be right. So then you want to go back and look at it. Okay? Any questions about this? Everybody get it? Who doesn't get it? So now, I want you to do it again. But this time, folks, the equation is a plus here, and this is T1 and this is T2. Okay? Plus T1 and T2. So it's the other one. The other one, the one I don't like. But I want to show you that you get them both.
It's P, not T. The change.
Or you can do either. Yeah. So just do it. Here's the information. This now becomes a plus, and this is a T1 and a T2. Who's got an answer? What do you get? 350. Same answer. What the heck? Yeah. And as Josette pointed out, we could have also said P1 over P2 here and made that a plus. There's lots of variations on Clausius Clapeyron, okay? Just make sure you used one and not a combination of the others, okay? Folks, if you want to use mine on the exam, that is how it's going to be graded. We will try and remind the graders that you can use, because the book, folks, uses the other one, okay? Every other book uses a different one. I use the one I can remember. So if you get the answer right, this wacky way, with this being a plus and this being a 1 and that being a 2, and you get 350, guess what? You get all the points. If you say 350K, you get the points. And they don't care how you plug it in. But you got to be careful, because if you use an equation that is not the standard one, which is the Don-Blake equation, then if you get something plugged in wrong, I'm not sure that the TA who's grading this is going to be so wonderful that they're going to go back and figure out, oh, you've done this and this and this, okay? So I suggest you use mine, or just get it right your way, okay? Okay, do this one. I want everybody writing. We got an answer? How much?
1520 torr, 1,500.
Something else, 500. Doesn't make sense though, does it? What's the question?
The question is, the vaporization was the vapor pressure I mentioned.
Okay, so look, we at about 58 degrees, we're at 405. At 25 degrees, we got to be a lot lower.
Okay, got it.
Okay, so you got a negative there. You forgot a negative.
Okay, got it.
Oh, what's a negative sign?
I hate it when that. Okay, thanks for much.
Okay, we got an answer?
111.
111 torr, he says. You know what? That seems reasonable. Why? Because look at this, at about 60 degrees C, it was 400. So if we get colder, what do we expect the vapor pressure to do? To go down. Okay? Did we get that answer? Now, unfortunately, I'm a little bit embarrassed. No, I'm not embarrassed. But they do it using the other one. Okay? So you notice they've got P2 or P1. They don't have a negative here, and they got T1 first. Okay? Same answer. Okay, you're going to get the same answer. So we've got that right side is equal to that. We got 107 torr. So folks, before you start throwing numbers into that equation, please just take 10 seconds to try and get a sense of what is the sign. You know, is it like entropy is going up, entropy is going down? This looks spontaneous, it doesn't look spontaneous. Or in this case, you're given 405 torr at a certain temperature and we're colder. Okay? Okay. Here's a problem. You ready? Write it down. This is the equation you will use. Well, let me ask you a question first. How many got that last question right? Ooh, okay. Okay, here we go. What is the delta H of vaporization for a compound that has a vapor pressure of 20 torr and at 20 torr and 20 C, okay? And a boiling point of 100 C. What is delta H of vaporization? 20 degrees C, 20 torr vapor pressure. Boiling point of 100 C. What is the delta H of vaporization? Yes? I was waiting for somebody to ask that question. Oh, bad question, folks. Here's the question. Thank you for asking it. The question was, what is the other pressure?
760 torr.
What's the definition of a boiling point, folks? Didn't I tell you that like about 36 minutes ago? Huh? If you have 20 torr at 20 degrees and the boiling point is 100 C, the pressure is 760 torr. Jeez. I sort of tricked you. But you had the information, folks, okay? It's very important that you think about questions. I know the answer.
Is 41,295 joules per mole, or 41 kilojoules per mole.
This guy tried to be like water.
Yeah.
Yes? 41 kilojoules. Very good. I tried to make it kind of close to water, okay, so that I wouldn't screw it up too bad and I'd actually have a clue as to what the answer was going to be, okay? So folks, if you're not given something, it may be because you already have that information. So once again, is anybody going to get fooled again if I say that the boiling point for something is 300 degrees C? What is the vapor pressure at that temperature? What is the vapor pressure of anything at its boiling point? 1 atmosphere. It just boils. That's what it means. It's when it goes from being the liquid to the gas and it boils off. That is the definition. So do not be fooled again. So I never again have to say what the pressure is. I don't, like in the first problem I said the boiling point of 760 torr. I was being nice. Okay? I'm not going to be nice from now on. I promise it. Okay, so now a question I have for those, a lot of people raise their hand that they got this one right. How many didn't get this one right? And how many, okay. So, how many got it to this point? Okay, so look, you were given the delta H, you know what R is, you were given this and this, and you were given one pressure. How many of you know, but you had a log of P something over P something, and you knew what one of them was. How do you deal with, you had on this right side over here, you had a minus 1.33. Minus 1.33 is equal to log P2 over P1. How many know how many don't know how to get out of that situation? Okay, remember the other day, I asked you to find the factorial button on your calculators. Does anybody remember where that factorial button is? Do you remember when I asked you to do the factorial button? Please say yes. Okay. So now, folks, there is probably algebra. Probably we learned this in algebra, I'm not sure. A way to get something out of being a log. Okay? How do we get this to not be a log anymore? If I just want this to be P2 over P1, what do I have to do to that log? Yes, that guy. Raise it to the e power. That's correct. So if I raise this to the e power, this side then just becomes P2 over P1. But then I have to raise this to the e power. So I want you to find your e button and go minus 1.33 to the e power. So you're going to raise e to this. And you might notice that the e power, sometimes the e button and the log button, the ln button, are on the same one. You just have to hit a different function thing because they're just the opposite of each other. Okay? So, what is e to the minus 1.33? What is it? Can you find it?
2.6.
She says 2.6. How many got 2.6? So e to the minus 1.33 is 2.6. So now on this side we got 2.6, and then we just say P2 over P1 is equal to 2.6. 0.26. Okay. Good. So P2 over P1 is equal to 0.26. Can you solve that now? What did we know? We knew P2 or P1? I forget which one we knew. We knew P1. So now it's going to be P2 over P1 is equal to 0.26. Okay? Cross multiply, solve for P2, and you end up with a value that is something. Okay? So folks, that little simple math stuff that we learned, we cannot forget. Okay? Because you're going to be getting something just, I promise you, something like this on the exam, where you're going to have to hit that E button. So you better remember where that E button is. Okay? Okay, this one. Do it. So just so you know, delta H, since you don't have that table, delta H is 45 or 43.5. Okay, for this equation. Oops. There. So delta H is 43.5 kilojoules. She's supposed to be in this one, but since they're the same. So. Yes? Isn't that what you're supposed to be estimating? You want me to tell you the answer? Ugh. Another trick.
What date?
So what you wanted was what is, you got it now?
Yeah.
Okay.
How do you convert kilopascals?
Okay, that's a good question. How do you convert kilopascals to, this is 101, or the boiling point is 101, let's just say 101 kilopascals.
That's what it is.
So boiling point, 1 atmosphere is 101 kilopascals, yes. Doesn't matter. Folks, it doesn't matter which one as long as you stay consistent. As long as you say, okay, look, I know that the vapor pressure at this is this. This could be T1, P1, or this could be T2, P2, as long as you don't mix them up. It's a very forgiving equation, folks, okay? Once again, folks, the hint is when they want to know what is the normal boiling point, that means when is it 760 torr. Now the trick is that they give this to you in kilopascals. So you just have to know that 1 atmosphere is 101 kilopascals. Okay? It's a little cheesy. Do we get 350? Once again, they've used it. They used the other equation. Doesn't matter. Same answer. If you plug everything in correctly, once again, they've got a different T1 and different arrangement, and there's a negative sign in there, but it doesn't matter. You're still going to get the same answer. Who got it? Who didn't get it? Who's still working? Okay. It's okay, folks, to be slow now. But it's very important that you do this enough times with enough permutations where you're given the 2 temperatures and a pressure, where you're given the 2 temperatures and the 2 pressures and you figure out delta H, or whether you're given all these different permutations when you got to take the E. All those things, so that when you get to the exam, no surprise. Okay, are we done? Who needs more time? Okay, if you need more time, then do it at home. Okay? The point is folks, you absolutely, this is a guarantee. If anybody doesn't get this right on the exam, I'm going to be almost as mad as if you don't get the last page right. Okay? Because I am promising you Clausius Clapeyron will be on the exam. I promise. If not one question, two questions. I love Clausius Clapeyron because I understand it. I can do Clausius Clapeyron problems. I got a little bit of a problem with that delta S total. Okay, let's call it quits.